Welcome back, everyone. This is lecture 13, part 1. I think there will be only one part to this lecture. And we shall continue with work of Cantor, which is discussed in some more in last chapter of the book, and I think this is chapter 13. So this will also be the last lecture for the class. Okay, so last time we proved that the cardinality of the set of real numbers is strictly larger than the cardinality of the set of counting numbers. So differently stated, this means, as we mentioned before, that the reals are uncountable, more reals than you can count. So the sizes of these two infinities are actually different. So from there, Cantor went on proving things about different sizes of infinity, and they are more or less of the same flavor like the previous proof. So before I move on to the so-called power set theorem, or Cantor's theorem rather, and we'll discuss a little result in some numerical details. It actually is a theorem, but we'll give again a numerical demonstration just to give the flavor of the proof rather than writing the formal proof. So Cantor also proved the following. Cardinality meaning the size, cardinality of points inside a square, cardinality of points inside a square, it is exactly the same as the cardinality of points in a line segment. Inside a square is the same as the cardinality of points in a line segment. So in some sense we're moving from a one-dimensional infinity to a two-dimensional infinity. So line segments, by a line segment here we mean just a chunk of the real line, or some open interval that is made up of nothing other than real numbers. And inside a square, for the sake of simplicity, we shall discuss the cardinality of points inside a unit square and the cardinality of points on, let's say, a unit interval. So let's say that you have a unit circle, not a unit circle, but a unit square here. So let's say 2, 3, 4, 5, 6. Okay. So let's say that this is the unit square. So this is of some, it doesn't matter what the length of this is actually, but let's say this is the unit square. So if you take any point in the unit square, let's say this point here, any point in a two-dimensional space or in this unit square, it is made of two coordinates, x and y. And the numbers x and y are actually what? They are real numbers. So the number x will come from this number denoted on this part of the real line, and number y will come from so here's number x and here's number y. So since these two are real lines, then x and y are some real numbers. Obviously between 0 and 1, because we are considering the unit circle, the unit square, sorry. Okay, so x and y, again I repeat, are some real numbers between 0 and 1, because we are in the unit square. So we want to compare now the cardinality of points between the unit square, or points that are in the unit square, and points on the unit interval, meaning on the open interval 0, 1. Okay? So if we pick any point here, if we pick any point on this unit interval, this point is just some real number, bit greater than 0 but less than 1. So it has only the x coordinate, it's only one coordinate. Whereas any point here is made of 2 coordinates. So at the first look it seems like there are a lot more points on the unit square than there are actually on this line segment, or are there. As it turns out, the cardinality of points inside a square is the same as the cardinality of points in a line segment. So to establish this fact, we have only one tool from last time, and that is establishing a one-to-one correspondence between points on this line and points on the square. The moment that you actually establish a one-to-one correspondence between the two, then you can say that this unit square point-wise is of the same cardinality as this unit interval, again point-wise. We're not talking about areas, lengths, or anything like this, because these are obviously two very different objects in different dimensions. So we're not talking about this concept. We're simply talking about the number of points that this unit squared is made of, which is basically real numbers, and the number of points that lie on this unit interval, again, they are real numbers. Okay, so let's talk about a particular example, and that will actually just give you the scheme of things. And it will not normally be a formal proof, but this is what you do. So let's say that you have some point xy on. Let the point xy be in a unit square. So what are the coordinates of this point? I don't know what they are, but let's say that they are some real numbers between 0 and 1. So this x here is some real number. Let's say this is number 9, 8, real number 9, 8, 4, 4, 3, 0, 2, 0, 0, 9, 8, 5, and so on. Let's say this is some real number pertaining to coordinate x here, and this other number also would be another real number between 0 and 1, and let's say that is 0.444309233, and so on. Okay, so I need to find a pair. Meaning I need to pair this point in the square with a particular with some point on the unit interval. Whatever I'm about to do surely works for absolutely any point in the unit square. So if you pick any point in the unit square by doing what I'm going to do in a minute, you can pair up that point in the unit square with some point on the unit interval here. Okay, so I want to establish or I want to find a pair for xy. So this be a point in the square. Okay, so and we want to pair it up with some point on this unit interval. Let me call that point z, and I don't know what this point should look like. So here's how you find this point z here on the unit interval. You use a shuffling method. Obviously, z will be again a number greater than 0 but less than 1, so it'll start with 0 point something. We're always talking about the decimal expansion of these numbers. Okay, so z will be created as follows. We'll shuffle digits between x and y. That means the first digit after the decimal point here will be this one, and then the next one, and then the first digit after the decimal point, this one. The second digit after the decimal point will be the 4. So I have 9 from here. The second digit would be 4. The third digit would be 8. The fourth digit would be 4. And then I have 4. And then I have 4 again. And then I have 4 again. And then I have 4 again. And then I have 3. And then I have, let's make this 9, it doesn't matter. So it doesn't look like I have a pattern of sorts here, because I don't. So where was I? We are at the 3. So far I have used 9, 8, 4, 4, and I've used 3, and here I've used 4, 4. I'm having more 4s here than I should. Okay, so this should be 3. And then the 0, and then this other 0, and then the 2, and then the 9, and then 0 red, and then 2 blue, and so on. So you get the idea. You get the idea. So to create this other number on the unit interval that you are going to pair the point with the square, you simply shuffle the digit, one from x and one from y. Again, when I'm talking about the digits, I mean the digits after the decimal point. So 9, then 4, then 8 and 4, then 4 and 4, then 4 and 3, and so on. So you take one digit from here and one digit from here. Okay, so you got a pair, and that should work. So this is obviously a real number. Surely it is greater than 0, but less than 1. So certainly is somewhere here. So this point here, given by these 2 arbitrary coordinates within the unit square, can be paired up with this other point in the unit interval. So the question is, can you do the same for absolutely anything in the unit square? Sure you can. So take any point in the unit square, do the shuffling, and then you'll come up with a point on the unit interval. Okay, is that a one-to-one correspondence? The answer is almost there, almost yes, but I'll tell you what the problem is in a minute. So, okay, well, so if you pick something on the unit square, you certainly can find a pair in the unit interval. What happens if you pick some number on the unit interval? Can you find a pair for it in the unit circle? My apologies, I don't mean unit circle, I mean unit square. The answer is yes. How? Well, you can unshuffle it. So if you are given, so let this be a point in a square, then by shuffling digits, between decimal expansions of x and y, we get z. We get point z. So that's how you get the point z. Okay. So given any point on the unit interval 0, 1, I mean the open unit interval, we can unshuffle it to find the pair xy in unit square. For example, so let z be this number, 0.57, 89, 0023, 58, 57, and so on. Then this is paired with which point on the unit circle? According to this rule, this will be paired with the following point. Okay, it'll start with a 0. Your x and your y also will start with a 0. Then the x will come from here. So 5, 8, 0, 2, 5, 5, and so on. And this will be, the blue ones will be the decimal expansion of the y coordinate. So 7, 9, 0, 3, 8, 7, and so on. So the shuffling procedure guarantees that if you take absolutely any point in the unit square, you can find a point on the unit circle, and if in the unit interval, and if you take any point on the unit interval, you can find a pair for it in the unit square. So is there really a problem with this procedure? Slightly yes, but we can come around it. So let me give you an example. So let's say that, so here's an example. When the shuffling when this shuffling method does not work. But you surely can come around it by twitching this procedure a little bit, as you'll see in a minute. Okay, so let's say that you have the following number. Let's say that your number z is the following number: 0.46909090, and so on. Okay, so with what point on the unit circle this, with what point xy on the unit square, my apologies, this will be paired up with? Well, let's see. So the x coordinate will come from the red ones, and the y coordinate will come from the blue ones, the underlined, that is. So what we're doing is, as I said before, given any point on the on this line segment, to find a pair for it in the unit square, in the square, you simply unshuffle this. So that's exactly what we're doing to find the pair for this point in the square. So let's unshuffle, then you will have what? You will have 0, 5, 9, 9, 9, 9, obviously with 9's never ending, and the y coordinate will be 0.6000 with zeros never ending. The problem with this is that this point xy, given in this representation, it's exactly the same as the following point. We all agreed last time that 0.600 can be written as what? As 0. What are how that can be written? That can be written as maybe I should make this a little different. My apologies. Otherwise, nothing wrong with this example, but let me make this a 4. Not to confuse you. So that's a 4. Alright, the problem is a 0.6, it is the same as what? As 0.599, 9 with 9's never ending. These two are the same number. So we're saying that point Z is paired up with this point xy, but this point xy is the same as this point xy. So this point Z is paired up with this point xy in the square. However, if you were to actually shuffle this by this method, this point according to the shuffling method, according to the shuffling method, should be paired with what? So if you shuffle this, you'll get the following: 0.45999 with 9's never ending, or 0.46, and 0.46 is very different from 0.469090 and so on. So what went wrong? So it seems like this point cannot be paired with this point in the unit square. So how can one go about this? Here's what we can do. When going back to this shuffling method, instead of shuffling the digits one by one, 9, 4, 8, 4, 4, 4, and so on, we are going to shuffle blocks of digits. So will not be one digit at a time, but it will be blocks of digit at a time. So what should govern, so to speak, those blocks? I mean, how long they should be? Is there a pattern? 3 digits, 4 digits, and so on. So it all depends on the zeros. The moment that you hit a 0, whenever you hit a 0, you are not going to just shuffle that 0. So if you don't see a 0, then you'll proceed as usual, one by one, 9, 4, 8, 4, 8, 4, and so on. But the moment that you hit a 0, you are not just going to shuffle that 0, but you are going to take the 0 together, or the 0 or the string of zeros up to and including the first non-zero element. So when it comes to you actually shuffling the 0, you're not going to shuffle just the 0 and then something else from here, but rather the entire block of 2. 0, 2 will come together. 0, 9 here will come together. So let me just write the rule here once again, and let's see if we can do it with this point. So, here's a problem. So this is a problem. Okay, so to fix this, when we shuffle, we group all consecutive runs of zeros together with the first non-zero digit. So back to the original example. So for the same xy, z will look different. Then z would be what? Would be 0 point. So I'll take 9, 0 point, 9. So this is the first digit. Then the second here is 4, then 8, then 4, then 4, then 4, then 4 again, then 3, then 3 again, then 0, but not 0. I will not take 0, I'll take 0, 9. I'll take 0, 9 here, 0, 9. Then coming back to this, I'm not going to take just 0, I'm going to take 0, 2. Then I'll take 2. Then I'll take not just 0, but 0, 0, 9. Then 3. Then 8, and so on. So not this number, but this number. You are going to group together 0 with 2 or 0 with 0, 9. So the groupings or the groups of the blocks of digits will always be of a different magnitude. I mean, they will all be different, not necessarily one digit or 2 or 3 or whatever the number is. So will this work for this number then? So let's see, if we go according to this, then, so here we back to the original example, and now example 2. Example 2 should work. For example, when you do this, when you use this way of shuffling, you will get what? So given the x, y to be 0.499 with 9's never ending, and 0.600 with zeros obviously never ending, to what point z this will be paired up with? So 0, and then you have number 4, and then you have number 6, and then you have number 9 here, and then you will take a 0 here. Why only a 0? Because this is just a string of zeros with nothing else, so there is no first non-zero digit after this, so you just simply take the 0, no choice, and then back to 9, and then back to 0, and then back to 9, and so on, which is exactly this number here. So this is how you get around this little problem. So simply, not simply, but this proves that the cardinality of points between a square, points in a square and points on a line segment is also the same. So this concept of infinities on 2 dimension and 1 dimension being the same is established by this little proof. It's not a formal proof though. So anyway, this will be end of part 1, and then on part 2 I'm going to talk about the Cantor's power set theorem. I'll be back in a minute.